agenda are 2 short talks by some of our industry colleagues who are going to share some things about their own work. So here we'll start with James from Adobe.
All right. So to start, I want to thank Justin and Mina for organizing this wonderful event. Thank you guys. It's good to see so many of you today here. So I'm very grateful for this opportunity to talk about our research lab and some of my own work. So my name is Qingnan James Zhou. I'm coming from Adobe Research. I'm a senior research engineer. So if you are not familiar with Adobe Research, I'm going to play a very quick promo video. So hopefully that will clear things up.
So in Adobe Research, we talk about inventing the future. This is a complicated endeavor. It involves understanding what is or will soon be technically possible, to imagine how that might be used for some workflow or purpose that our customers care about.
One of the coolest things that as researchers we can do is develop technology that then can be used and is used by millions and millions of people.
One thing that I find really exciting about Adobe Research is that it feels like researchers aren't really limited in terms of what they can implement, what they can build, where their creativity wants to take them.
So we have a lot of freedom to do what we think is important, and that makes us more motivated.
We are just one message away from starting collaborating in any topic that we find it could be interesting. So that's something that I value a lot personally.
We might also see research helping people with much more mundane things like quality of life improvements inside products where we're helping them do things a little faster.
We actually encourage academic publication of our cutting-edge research, partly to attract and retain the best talent at Adobe, and also to test our ideas against the scrutiny of peer review at academic conferences.
We're encouraged to participate in the broader academic communities, and so we are recognized and rewarded for being, thought leaders.
I think this constant interaction between the company and academia is really enriching and brings a lot of ideas for us. It brings a lot of technologies.
How could this actually help a user? Or how could this be turned into a feature in a product? I guess as a research engineer, that is a focus for me.
One aspect of Adobe Research which is foundational to how we work is what I call the virtual team. And this includes our intern program, where we more than double in size, usually in the summer, where we have an influx of very talented interns. And we don't treat them as people to do existing tasks, but more to come up with new ideas and take risks and explore new concepts.
It's amazing for us as researchers because we get to work with such brilliant people who get to explore, amazing ideas.
So Adobe Research has a very vibrant intern research program. It creates a huge talent pool and fresh ideas we can tap into.
So often an intern will return to their school and we'll collaborate even further, leveraging new ideas, helping us scale our connections and therefore also our creativity.
So it's just exciting that we have such a program that working closely with interns and continue kind of drive innovation inside and outside Adobe.
I think whatever we are doing, it has a lot of potentials for impacts across multiple forums, and that has been the real driving force of what we have been doing.
Adobe Research was founded to give us space for us to explore cutting-edge technologies that might go into future versions of Adobe products. And as it's grown, we've established a mission to look into the future, to see what's coming, to figure out what will be useful, and then to try to understand how to sculpt that into useful tools for our customers.
We are
Adobe Research.
Adobe Research.
Adobe Research.
We are Adobe Research.
All right. Thank you. All right. So in summary, Adobe Research is a great place to do industrial research. We try to connect research, cutting-edge research with cutting-edge Adobe products. We collaborate widely with universities and academic institutions, and we publish at all major conferences and journals. And lastly, we have a very awesome intern program. So the next part of my talk will be focused on a small corner of Adobe Research, which is like my focus. So at Adobe Research, I mainly focus on a geometry processing library called Lagrange. So with the emphasis, this is a robust geometry processing library. Our mission is to connect cutting-edge research with cutting-edge Adobe products in 3D. So we want to serve as the bridge that connect the research technologies that we see, for example, at SGP with the product need. So with Lagrange, we are integrated into multiple Adobe products. So if any of the logo looks familiar or unfamiliar to you, so from left to right is Adobe Dimension, Adobe Substance Stager, Designer, Modeler, Sampler, Illustrator, and After Effects. So some of them are under the umbrella term of Substance products, so focus on texture painting, texture generation, and model generation. And Illustrator and After Effects are basically vector graphics application and video editing software. So surprisingly, all of them has some need of 3D geometry processing, and Lagrange is supplying those functionalities. So as a byproduct of that, we try to borrow the practice from our product team partners to develop Lagrange. So we use industry production development technology or practices such as code review, unit test, CDCI, etc. in our own work. So one of the things very interesting for Lagrange is it is built out of the box. So it may sounds easy, but once you have lots of dependencies, and once you have a growing list of functionalities, a software package is very easy to grow bulky. That makes building one of the main obstacles. So for Lagrange, we have a very sophisticated CMake modularization system. So you can enable, disable different modules. That way, product team can only enable the module that they actually need to use without building everything in bulk. So we also provide a very easy to install Python binding, so you can pip install Lagrange in one command. So at the core of Project Lagrange is our polygonal mesh data structure. So in contrast to many of the common popular open source representation for meshes, we do not use vertex array or triangle array or face array. So instead, we have this data frame concept. So we treat each individual mesh as a data frame. So in a data frame, it contains the geometry. So that means vertices, triangles, and polygons, etc. But also the attribute associated with them. So we support attributes that's sitting on the vertices, edges, facets, corners, and index attributes such as UV, and lastly, also value attribute. So the advantage of having advanced attribute support is when we do geometry processing, such as mesh cleanup, we are able to propagate attributes from input to output without the user ever need to worry about it. We also support I/O for all the popular mesh formats, including both single object mesh representation as well as scene representation. So here are some of the popular formats. So among them, PLY, MSH, GLTF, and GLB, they all support attribute storage, which we leverage heavily in our debugging process and in our development process. So another interesting aspect of Lagrange is when we design this data structure, we try to minimize the amount of copy we need to do when we interact with other either product code bases or other third-party libraries. So in particular, we try to enable copy-free interoperation with a popular framework like Eigen or libgl. So on the Python side, our buffer can expose as naturally as NumPy array or PyTorch tensor without ever copying the data. So this is one of the focus of the project. And lastly, our project is fully open source, or not fully, partially open source. So you can find all the information in the documentation page. You can also git clone our project code base. Or if you want to, if you're in the Python world, you can pip install Lagrange open. Our license is Apache 2, which is a commercial-friendly license. You are free to use it for any purpose you want. So that concludes my talk. And if you're interested in opportunities at Adobe Research, please feel free to talk to me. So obviously, as I mentioned, robustness is one of the issues. So in research world, we often care about proof of concept. We want to generate beautiful examples and prove our idea works. But in industry, we actually need to handle whatever input our customer give us. So that means handling all the corner cases, degeneracies, etc. So robustness is really the key to make a technology that never fails. So that's like one of the major takeaway from industry perspective. The second perspective is efficiency. Sometimes we are willing to sacrifice efficiency a little bit because we are not trying to be the fastest, or some of us are not trying to be the fastest. But in practice, there is like the latency is really important. So there are a lot of work going in to make a particular technology very efficient and parallelizable. Yeah, so that's another thing. Yeah.
Okay, so today I'm just going to highlight a few applications of where geometry processing is being used to make your next car. I work at a company called Altair. We make engineering simulation software. Physics simulation has become a cornerstone for how we design vehicles in the last few decades. And you can see there's virtually anything that can be tested physically can be simulated, and this has been a huge step forward, but there's still room for improvement. So today I'll show how some methods that you know and love in geometry processing are making this workflow cleaner. And it starts with the PDE itself. So as I'm sure you're aware, we can simulate a full vehicle crash at a high fidelity, but to do this with the finite element method, it can take 12 hours. Which means once you've made a design change, you have to wait 12 hours to see if it was effective. Traditionally, the way automotive companies deal with this is through surrogate modeling. So they pick a few design changes that they want to vary, they sample them, and then they fit a curve to the results. So it turns out these surrogate models are pretty short-lived. You can imagine that your parametrization changes. Maybe I've added this bracket, and now I want to study its position. I kind of have to throw away all of my previously sampled simulations and start from scratch. And then there's this concept of historical simulation. That's what the automotive companies call it. You can imagine decades of simulations that are kind of just sitting on the shelf. How can we use them? So now comes these new methods for learning on manifolds themselves, and both the geometry and PDE communities have contributed here. So we're learning methods to be able to go from the initial shape to the final PDE solution. We want those methods to be equivariant to rotation and to discretization. And some challenges we have in our space is we deal with quite large meshes that can have 100 million nodes. We use 1D, 2D, and 3D element types to represent various components on a car. And now that we've moved away from the parametric space, there isn't a clear notion of what's interpolating and what's extrapolating, and so we want to be able to quantify our uncertainty in the prediction. We released a product last year for training deep learning models on simulation results. So in this workflow, you can imagine I've already trained a model. Here an engineer is bringing in a hood model, and they're going to click predict. This red sphere actually represents a human head. This is a pedestrian safety simulation that all car companies do. And within a few seconds, we predict the result. And so you can imagine this just allows engineers to try way more ideas than they could with finite element alone. And we see nice agreement. So the next one has to do with actually setting up the finite element model. I didn't know this before I went into industry, but there was significant manual time spent building finite element models from CAD, and that's measured in days sometimes. And you can imagine that those human hours are more expensive than the compute hours required to solve the PDE, and so we spent a lot of time thinking about how we can automate this process. So what are those engineers doing? They're simplifying geometry, they're removing fillets and logos and holes, mid-surfacing, they're then connecting components with welds. And you might wonder, why isn't this automated already? And the reason is that this logic is often part-specific and even company-specific. Each one has their own standards. So the shape analysis tools that you know and love can come to the rescue if we can classify sub-assemblies, and then within that parts, and then within that perform segmentation and find features. Now we can start to apply these company-specific rules in order to automate the FE build process. So some challenges we face here are what we call unclean CAD. We have sliver surfaces, duplicate surfaces, poor connectivity, and then also data scarcity. So someone earlier brought up that, engineering companies aren't willing to share their data because it's intellectual property, and so we don't have a lot of data to train on. But here's another commercial solution. In this one, you can see the user is manually labeling a few parts on a car. You can do this for a few different cars. You might label them by which subsystem they're in, which manufacturing process you're using. And then finally, we can train a simple classifier and apply that classifier to a new design. You can see this assembly consists of over 1,000 parts, and we can start to automate through recognizing a part. Now we can automate the FE model build. And then the last application deals with generating new shapes. So the status quo here looks like one of two flavors. One is this classic shape optimization. So here the engineer is choosing some design parameters that they want to optimize. And the weakness with this is that we have great optimization algorithms, but at the end of the day, the final design is only as good as the parametrization that you could come up with in your head. And then there's also methods like topology optimization, but they don't exist for all types of physics. And also, we're interested in leveraging some of the knowledge from the decades of historical designs that we have. So you could imagine a data-driven process, and as I'm sure you're aware, there's this explosion of methods for doing generative modeling in 3D. We saw some awesome ones from Microsoft today. But the way I see it, this learned latent space from historical designs is just another design space, is just learned rather than explicitly dictated. And we can use all of these great tools we have for exploring latent spaces. So we collaborated with a group here at MIT. This is Caitlin Mueller's group, and Manadeep did the work. So here we're taking models from the SIMJA bracket dataset. We have trained a generative model to create implicit geometry. And then we're interpolating between two designs. And you can see all of the interpolated results also look like brackets. Next, we want to take this a step further. We're not just looking to generate realistic-looking shapes. We want to find the best one. So we're really trying to solve an inverse problem. And it seems with these generative methods, there's a trade-off between how novel the designs look and and whether or not they're feasible to construct. So I think these are current challenges that the generative 3D applications are facing in engineering. This is the commercial bit. We work with a lot more than just cars, so just about everything that gets made, from planes to phones to submarines, is simulated. Personally, I found it a quite rewarding place to work across all these industries. We have offices all over the world, and it's been a really rewarding place to work. So to the students, if you're interested in internships or full-time, feel free to reach out. And to the academic labs, we do a lot of interesting collaborations and be happy to work with you. But thank you for your time. the methods that you guys come up with have so much application in the engineering world, but sometimes it feels like there's a language barrier. And I've found it quite interesting and rewarding to kind of work in the interface of the two. But particularly for data-driven processes, data scarcity is a huge problem in engineering. That 3D designs are gold for these companies. And so I would say if you're working on any data-driven process, focusing on methods to make it really data efficient will make it more applicable to my field.